slide, please. Right, so the typical experiment that you make when you prepare a nanowire is to measure its conductance by applying a voltage across it and observing the current that's flowing. And as far as we're concerned, we don't call anything that we make a nanowire unless we can measure a conductance. But more than that, we also insist that for it to qualify as a nanowire, the current voltage curve should really look like the left-hand side. So the sketches here show something that we would call a conductor on the left and something that we would call an insulator on the right. So on the right-hand side, you can see that there is some current flowing. The blue curve shows that large positive voltages, we start to see some current flow. But we wouldn't really call this a conductor rather, because there's essentially no current in the middle region. In fact, if you just look up what is the breakdown voltage for air, you'll find that for dry air, 30 kilovolt per centimeter is the breakdown voltage, and therefore that's 3 volts per micrometer. And so when you work on a very small scale, you can almost always generate some current by applying a high enough voltage, whatever you have between the electrodes. So we will call the things that we make a nanowire if we see something that looks like the left-hand side, where for any small voltage, we get some current flowing. We can state this as the slope of the current voltage curve near the origin, near 0 applied volts, should be positive. So we're looking for a non-zero differential conductance. On the right-hand side, this slope is basically 0 at the origin, and on the left-hand side we have some value, so we would call that a conductor, and that object might be a nanowire. So if we look at DNA next, so on the next slide. Yeah, so there's quite a lot of work published in the literature describing electron transfer processes within DNA. And what people typically measure by a range of techniques like photo-induced electron transfer is the decay length of the electron transfer rate. So the little arrow indicates a probability of making a transition from one place to another along the chain, and that decays exponentially with distance z along the chain. And people have reported various different beta values, and the smaller is beta, then the further along the chain the electron will go. But even for very small beta values, so about 0.01 per nanometer, the chance of such an electron transfer happening over micrometer lengths is basically 0 because of the exponential factor. So DNA itself doesn't really behave as a nanowire in the sense that we're after. We can't flow current through it over micrometer lengths. So if we go to the next slide. Thank you. So this is the cartoon of what we do. On the left-hand side is the familiar double helix of DNA. It's about 2 nanometers in diameter, and you can obtain very, very long lengths. And over small distances, you can have electron transfer, but over large distances, this is very insulating. And so on the right-hand side is data that we published some years ago. It's certainly not the first example of this data, but we needed to remind people, in fact the reviewers of that paper, wanted to know why did we bother coating our DNA molecules to make them conductive. And if you look at the current voltage curve there, you can see essentially zero current for a range of voltages of plus or minus half a volt. In fact, the current level there we know is less than 10 femtoamps. So DNA itself, and this is measured over a distance of about 2 micrometers in length, is very, very insulating. What we do to make nanowires is we use DNA as a template. We're not exploiting any electrical properties of the DNA itself, but what we are using it to do is to control the way materials grow and induce them to form in as long, thin objects, and to make nanowires by this process. So the cartoon here shows the DNA being coated with this pale blue area, and that's meant to illustrate how we hope to induce the formation of nanowires from materials that don't normally grow into long, thin objects. So I think on the next slide, I'll say a little bit about the template that we use. So all of our work is done with, or almost all of our work is done with Lambda DNA. I don't know how well the AFM image at the bottom right of this figure shows up, but if you look carefully, you can see white lines of material going from the bottom left to the top right corner of that image. Those are single molecules of DNA. So we use Lambda DNA, which is isolated from a virus that infects bacteria, bacteriophage, and the reason for this is it's available in high purity. It's a very well-defined length. It's exactly 48,502 base pairs long. It's about 16.7 micrometers long, which you can see just about in the AFM image. And the other important thing about DNA as a template is it's a very stiff polymer. Most synthetic polymers are too flexible and they exist in solution as a random coil, and if you were to template on those, you end up with a particle instead of a nanowire. So we need something that's relatively stiff. It doesn't coil up too much. Okay, next slide, please. Thank you. So here's a series of examples of different inorganic materials that we make. Oops, too far. Yeah, thank you. And the top line shows atomic force microscope images of DNA and copper on DNA. So these images are basically about 5 by 5 microns square, and on the top left this is an image of Lambda DNA, and you can see a single molecule running from the top of the image towards the bottom. The molecule is longer than the scanned area, so it crosses the whole image. And that's a single molecule of Lambda DNA, uncoated. So what we do is we would take Lambda DNA in aqueous solution, and we mix it with a metal ion, a solution of a metal salt, in this example copper nitrate, and then we add a reducing agent. So the reducing agent in this example is ascorbic acid, and it will reduce the copper-2 ions to copper metal. Now, the chemical structure of DNA is such that it has a large number of binding sites for metals. Metals will interact strongly with the negatively charged phosphate groups that form the backbone of the double helix structure, and some of the metals will also interact with the nitrogen atoms on the nuclear bases. But at any rate, in a solution containing DNA molecules, a large fraction of the copper will be bound to the DNA, and when it is reduced to copper 0, to the metal, it will then nucleate and grow along the molecule. So this is the sketch at the top right, showing little particles of copper metal forming on the DNA. And the atomic force microscope image at the top right shows, again, a DNA molecule, and I deliberately set the height scale on these two AFM images to be the same, so that you can see that the molecule on the top right is now coated with copper. It's much thicker, and so the height appears much larger in AFM, and it's a relatively long, smooth nanowire, and you can study its chemical composition by X-ray photoelectron spectroscopy and other techniques and confirm it really is copper metal. You'll also notice that there are some particles of copper metal that have formed off the template and are just precipitated on the surface. On the bottom line, we'll show you an example of how we make various binary semiconductors. So we can make a range of oxides and sulfides, and we do this by a very similar process. We take an aqueous solution of Lambda Dna, we add some of the metal salt. So in the particular example here of cadmium sulfide, we add cadmium nitrate, and a fraction of the cadmium nitrate is bound to the DNA. And then, instead of reducing the cadmium, we would add a solution of sulfide, so HS minus anions, and that will precipitate the cadmium 2+ as cadmium sulfide, CDS. And and so you can see in the 3 AFM images, on the far left is a larger area.
Dr. Beth, please unmute your microphone.
Oh, I'm so sorry.
Okay, no problem. All right.
Oh dear. Do you wish me to start from the beginning?
No, no need. Just continue, please.
I'm terribly sorry. Okay. The atomic force microscope images on this slide show examples of metal nanowires at the top and semiconductor nanowires on the bottom. The example at the top is a copper nanowire prepared by mixing copper 2 salt, that is copper nitrate, with Lambda Dna, and the copper 2 ions bind to the DNA molecules, which have many binding sites for metal ions, the phosphate backbone and the nitrogen of the bases. And therefore, when you reduce them to the metal, in this example with ascorbic acid, the copper metal forms on the DNA, because that's where the copper, a large fraction of the copper ions were bound, and so it nucleates and grows on the DNA template, and at the top right you see a copper nanowire formed by reduction of copper on Lambda DNA. And those two atomic force microscope images at the top left and the top right are given with the same size and the same height scale, so that you can compare the rather thick copper-coated nanowire on the right with the much thinner bare DNA at the top left. Okay, so we make metals by electroless reduction of the metal ion on the template, and we make semiconductors by precipitation of the metal ion. So the series of three images at the bottom shows cadmium sulfide on DNA, and the way this is done is you take an aqueous solution of You take an aqueous solution of Lambda DNA, you add cadmium nitrate, a large fraction of the cadmium will bind to the DNA, and then you add a source of sulfide to precipitate the cadmium ions as cadmium sulfide. And in this example, the image on the bottom left is a large area, the image in the middle is a zoomed in, and it shows the cadmium sulfide forming as particles along the DNA molecule. If you change the conditions, you can control this so that the nanowires are more or less smooth. So the image on the bottom right shows again cadmium sulfide on DNA, but this time a more or less continuous a nanowire of cadmium sulfide along DNA. And we can make sulfides and oxides of various kinds by this process. Okay, next slide, please. Thank you. So as well as metals and inorganic semiconductors, we can also make conjugated organic polymer nanowires. And if you take some of these heteroaromatic molecules, so I show you some examples here, the AFM image labeled A is polypyrrole coated over DNA. And pyrrole is the chemical structure is sketched in the top left. So pyrrole is just a 5-membered aromatic compound, slightly water soluble. If you oxidize that, it forms a polymer that is shown at the top left. And as formed, the polymer is actually cationic and interacts very strongly with the DNA. And you can make a whole range of different organic polymers. And the example at the bottom is a pyrrole, where a certain number of every nitrogen atoms of the pyrrole unit has been derivatized by a ligand. In this example, a bipyridyl ligand, and that can be used to bind metals. And we find that actually we can make hybrids. So example C is a thick nanowire prepared from Lambda DNA, which is first coated with this organic polymer that contains a pendant bipyridyl group, and then we do electroless plating of palladium, and palladium will bind to the bipyridyl group and then be electrolessly deposited as palladium metal on top of the polymer. So this is a hybrid which is sketched at the bottom right. First, we have an organic polymer in the center, and then around that is the palladium metal, and we can apply this to make a variety of different things. Okay, so that's the general scheme for how we prepare nanowires. So I'll talk a little bit about the characterization next. Next slide, please. Right, so the images I've shown are atomic force microscope images, and we usually make these by depositing a droplet of the dispersion in which the nanowires are prepared. So it's a reaction that happens in aqueous solution at room temperature, all of these reactions. We can take a small droplet, put it on the substrate that we use for AFM, and then we can drag the droplet. You can do this with the tip of a pipette, or you can blow it with nitrogen, or you can even simply tilt the sample so the droplet runs down the substrate. And when that happens, the DNA molecules are stretched out at the receding edge of the droplet, and this is why they on these images they look they show as long lines, because you can stretch them out by this process which is known as molecular combing. So if we go to the next slide, I'll show you a schematic of the process for making copper. Next slide, please.
I think it's still loading. Okay.
Okay, that's great. So this is an example of the preparation of copper in a little more detail. So at the top left, we in order to make this facilitate this process, we often silanize the silicon chip on which we're going to image. So we would typically start with a silicon chip coated with a thin oxide layer, and if we want to image single molecules, we don't want the surface to be too sticky to these nanowires, so we will then partially silanize it with trimethyl silyl chloride. So this makes the surface a little bit hydrophobic. We deliberately do not make it a completely hydrophobic surface. Then you can put a droplet of DNA solution on the surface and drag the droplets, or allow it to run down the surface. And you can either do this process directly with the nanowires prepared in solution, or you can first deposit the DNA on the surface, then you can then add copper and do the reduction on the surface. And in this example, it shows where the DNA molecules are aligned, and then copper solution is applied, and then the reducing agent, the ascorbic acid, and that eventually produces the nanowires at the bottom right hand side. So this is how we do the atomic force microscopy, which is one of our major techniques for characterizing these nanowires. Okay, next slide, please. Right, so what we think that many of our nanowires, not all, but many of them, have a structure similar to the cartoon at the top left of this picture, where the DNA molecule is coated by a series of particles that overlap. And one of the ways that we have of justifying this picture is we make two different measurements of the particle size. So in the example shown here, this is actually a cuprous oxide nanowire, and at the bottom right we can measure the diameter of those spheres just from the height in the AFM image. So we comb these nanowires onto a surface, either silicon oxide or mica. We image with the atomic force microscope, we measure the height of the features, and that is one estimate of the diameter of these particles, in this case about 16 nanometers. But we can also, if we prepare enough material, we can also obtain an X-ray powder pattern, and that's shown on the bottom left. And so for cuprous oxide, there are two major peaks. close to 2 theta of 36 and 37 degrees, and we estimate the diameter of the particles from the width of these peaks. So we fit the X-ray powder pattern, extract from the fitting the full width at half maximum, and use the Scherer equation, which relates the diameter of a crystal to the width of the peaks in X-ray diffraction to estimate the particle size. In this case, it comes out to be about 21 nanometers. And what we're showing here is that the diameter from atomic force microscopy and X-ray diffraction is of the same order. The X-ray diffraction diameter tells us about how big the crystallites are, and they're about the same size as the height that we see. So this is why we consider that this material looks like a series of beads on a string, the string being the DNA and the beads here being cuprous oxide. And these beads more or less merge together to form something that looks like a nanowire. We do have some examples where these two measurements don't match, and in that case we have a different model for the structure, but I can discuss that later if people have questions. So let's go to the next slide. Okay, so we know that our source of DNA has very precise length. It's exactly 48,502 base pairs long, but we don't always get nanowires that are exactly that long. This is just a curious example that one of my students found some years ago. This is a silver nanowire, and each of the squares that you can see is a single atomic force microscope image. And this was the maximum dimension of our scanner, about 15 micrometers on a side. And this molecule, which was prepared, this nanowire was prepared from Lambda Dna, is actually about 150 micrometers long. And what he did was he collected a number of AFM images and moved along the wire and managed to collect a picture of the whole wire. So this is not a common occurrence, but I just wanted to say that we don't necessarily make things that are exactly the length of the template, because it's possible that the material that we coat the template with can act to join up several different molecules. So this example here is certainly many molecules long. Okay, so I think if we go to the next slide, I'll say something a bit about the mechanism for these reactions. Okay, so we picture these as initially a series of beads, small, approximately spherical particles forming on a chain that is the DNA. And so we made a simple thermodynamic analysis of the free energy of this system. And what you can do is you say, well, if the radius of one of those beads is A, then the area of one of those beads is 4 pi a squared. And therefore the contribution to the free energy from the surface is 4 pi a squared times gamma, where gamma is the surface tension. So we can estimate the total contribution of all the surfaces of all the beads to the free energy by taking 4 pi gamma times the sum of the squares of the radii. But that's not the only contribution to the free energy of the system, because the material is adhering to the template. So on the simplifying assumption that the template goes exactly through the middle of each bead, we can say that there will be a favourable, a negative contribution to the free energy equal to the diameter of a bead times sigma, a line energy, which represents how strongly the material adheres to the template. So that's the origin of this formula for the free energy. So we have a very long template, and therefore it makes sense to talk about the free energy per unit length. So if we divide capital G by the length, we get little g. And then the other parameter that we control in our reaction is the amount of metal or polymer that we add to the solution. So if we know the volume of material that we're making, that is the total volume of copper or cadmium sulfide or polymer, and the total amount of DNA, we can talk about the volume of material per unit length of template. And the ratio of G to nu here is given by the equation at the bottom right, on the right hand side. And what we find is that we have two terms, one representing, of course, the surface tension, which is unfavourable. That tends to favour a state in which the material forms a single particle, and another originating from the adhesion of the material to the template, which is favourable, and that tends to favour the material covering all the exposed template, so forming a nanowire. And we have a constraint, of course. We have a fixed amount of material that we're templating, so we know the total volume can't change. And so the question is, what is the lowest possible value of this free energy per unit length? What is the state of the system which gives us the lowest free energy? And the answer is it depends a lot on how much material you have. If you have a large amount of material, if you are greedy and try to make a very thick nanowire, then it turns out that the term on the left, due to surface tension, dominates, and in the diagram on the bottom left, a large amount of material corresponds to a large value of average radius, and therefore the minimum is away to the right, where the radius has become very big, and in that case, what you really have is a single large particle sitting on the DNA. So this is very much like the well-known Savart-Beer-Rayleigh instability. That is, when you have a stream of water, it tends to break up into droplets because of surface tension. And it's the same kind of effect. The lowest energy state at very large volumes of material is a single large particle, because large spherical particle that minimizes the surface free energy. What is different in the case with the template is if you go to a lower volume of material per unit length into the blue shaded region, then actually the term on the right, due to line energy, dominates, and it becomes favourable for the system to cover all of the DNA. And that's actually crucial to making a nanowire, because if you have gaps between these particles, you don't get conduction. Okay, so if we go to the next slide, please. Here we are. Okay, so So what we've calculated so far is the situation on the bottom where we have a series of particles attached to the template, but you can also ask which of these two situations, a completely smooth cylinder encasing the DNA or the series of particles, which is the lowest energy state. And it turns out that the completely smooth coating is the lowest energy state as long as you keep the volume of material sufficiently small per unit length of template. So new in the formula is the volume of material, the volume of copper or of polymer or of cadmium sulfide per unit length L of the DNA. And so basically the first lesson from this analysis is if you try and make nanowires which are too thick, if you put too much material in there, if you have too big a ratio of material being templated to DNA, you don't get a nice smooth nanowire. So we go to next slide, please. So in fact we have a maximum possible thickness that we can make by this analysis. So if gamma is the surface tension between the material and the solution, and gamma subscript T is the surface tension between the DNA and the material, then the maximum thickness R sub C is the radius of the template, which is about 2 nanometers, times the ratio of these two surface tensions in absolute value. And if you put reasonable estimates for these surface tensions in, it tells you that you can't make nanowires thicker than about 20 nanometers on a single DNA molecule. And in fact, most of ours are somewhat smaller than that. The typical thicknesses are in the range 5 to 10 nanometers. Okay, so next slide, please. Right, so this is a series of atomic force microscope images that were acquired during the formation of a polymer called polydithionyl pyrrole, and it shows the evolution from, on the left, the early stages to the later stages of the reaction. So I don't want to mislead you. This is not the same DNA molecule being observed at different times. What this is a sample taken from the reaction in solution, deposited on a silicon surface, imaged, and then a later sample taken. So it's not necessarily the same DNA molecule, but it shows a typical progress of the reaction. On the left-hand side, if you look carefully, you can see a single DNA molecule running north-south through the image, which is a very faint line because it's relatively thin, about 2 nanometers, and it has a few particles of polymer growing along it. Not many, just a few. A bit later, after an hour or so, you see again a similar situation. There's a DNA molecule running north-south through the image, but now with a lot of polymer particles attached to it, and they're all quite a lot bigger. Actually, by this time, the polymerization reaction is finished. So all the monomer has been consumed by this time, but the process of templating doesn't stop there. If you look at the next image, what you see is that the particles of polymer on that template are starting to merge together. They're starting to reorganize themselves along the template, and our argument is that this is the material trying to minimize its surface tension, surface energy rather, minimize its minimize its free energy by adopting a shape which minimizes surface free energy and maximizes the adhesion to the template, the line energy. And after 24 hours in this case, you see a rather smooth nanowire. And so this we believe is the equilibrium state. And so we've been interested to try and understand a little bit more about the process that takes us across this diagram. So if we go to the next slide, please. Right, so the way we do this is we imagine a DNA template, and that's represented by the line labeled as the X coordinate. So there's a thick line there, that's our template, and we'd call that our X coordinate in this analysis, and the thickness in the radial direction is represented by this wavy line. It varies from place to place, and we'll call that coordinate R. So that's the thickness of our nanowire at a position X along the template. And we can make the same analysis of surface area against line energy, but this time it gets expressed as an integral over an integral along the template direction X in terms of the way the radius of the material changes with position. And that's the free energy, and the red dotted line is the equilibrium value when everything is smooth. And so I write the delta G as the difference between the free energy as it is now and the free energy at equilibrium. And then I can ask, how will this change? And use a standard assumption of non-equilibrium thermodynamics that the flux, the movement of material in the system, is proportional to this difference, to this driving force delta G. And we also have to, in order to make the mathematics tractable, we have to assume that there are no really steep places on the surface, no very large gradients. And if you do that, you can compute, starting from this model, you can compute a partial differential equation, which is underlined in red at the bottom, and this describes how the radius of the templated material R varies with distance x along the template and with time. And the factor eta, which is the last term on the left, is a noise term that I've included for completeness here, and the factor mu appearing in front of the two differential terms on the left. This is a constant of proportionality, which I'm afraid this analysis doesn't tell us what that is. We would have to do some sort of atomic calculation to get that value. But this evolution equation does let us simulate how the templating reaction goes. So if we go to the next slide.
Still loading.
That's okay. So essentially what we're going to do on the next slide is we start off with a system where we put beads of random diameter along a DNA template, and we just apply this equation and simulate it forward in time. And
Have you seen the next slide, Dr. Ben?
I can't see the next slide yet. At the moment, I'm...
Okay, maybe still loading. It takes too long.
would you like me to share my screen? Because I could probably bring this up on my screen.
Oh,
and then...
yeah, sure.
So let me just... Right, so let me do share screen. Okay, is that visible to you now?
Yes, I can see this.
Okay, so this now this now shows the simulation. So the black curve corresponds to a series of spherical particles at the start, and then we simply apply this evolution equation, and what we find is it predicts something very much like what we see in the atomic force microscope images. We go from the black curve gradually to the red and to the green and then to the blue at longer and longer times. And the second lesson we learned from this about making these nanowires is how slow this process is. Most chemical reactions approach equilibrium exponentially fast. This process does not. It behaves more like a diffusion equation. And so I guess the two lessons we learned from this analysis is, one, we mustn't be greedy about the amount of material we try and template. If we try and make thick nanowires, it fails. And you have to be patient, even though some of these reactions like the precipitation or the polymerization, even though the reagents are consumed very quickly, you have to wait for a long time, maybe up to a day or so, to form smooth nanowires, because the material has to be allowed time to rearrange on the template. Okay, so this is an example of the polymer, and this is an example also of the size distributions. So a series of atomic force images across the top, with the final material at the top right hand corner, which is quite smooth, and the line profiles labeled B, and the height distribution. So we measure the heights of all the particles and look at the distributions of diameters with time. And then the last row, D, is our simulation. And the other thing that we find is that this process naturally leads to a narrow size distribution at long times. So if you wait long enough, not only do you get smooth wires, but they also become relatively uniform in size. Okay. That has frozen. Why? Oh, there we go. Okay, so that's what I wanted to say about mechanisms. I want to just finish by talking about measuring the conductance of these things. So we have three ways of doing that, and two of them are sketched on this slide. So on the right-hand side, we make very small electrodes, a few micrometers in size, or the gap between a few micrometers in size. So what you see is optical image of gold on silicon dioxide electrodes that look like two fingers, and these we use to make contact to either end of one of these nanowires and study them by conventional methods. Those experiments are very nice if you can do them, but they are very difficult, and so my students really don't like this because it can take a long time to prepare a device so that you have the nanowire bridging the gap between the two electrodes, like in the AFM image at the bottom right. You get a lot of information if you can do this experiment, but it's really not very easy. People often prefer to do measurements with the atomic force microscope. So if you have a metal-coated AFM tip, what you can do is you can dry a solution of the nanowires down onto a surface, and it will form a dense mass that looks like, in the AFM, it looks like a plate of spaghetti or noodles or something that has just been spilt on the surface. But at the edge of that mass, you'll find one or two nanowires which poke out. And you can contact those individual nanowires with the AFM tip, and you can make a second electrical contact to the main mass by hand, just with a toothpick and some eutectic. And so you can actually study individual nanowires by that method. So I'll show you some examples of data. So this is from the Microelectrode Experiment. It's very nice because if you can do it, it's not such an easy experiment to do. You can study the temperature dependence. So this is from some work where we were studying polyindole nanowires, and we find that most of our conductive polymers show Arrhenius behavior, that is, they show activated conductance that increases as the temperature increases, and the beta value is 1. This is slightly different from what you see in bulk, where most conductive polymers show variable range hopping behavior, where beta is a half or a quarter. And in fact, with many metals, we find that as nanowires, they also do not show typical behavior. Some metals show very poor conductivity, and some show, again, a conductivity typical for granular metals, where the conductance actually rises with temperature, which is the opposite to bulk behavior, and this is typically associated with activated electron transfer between individual grains. So this sort of measurement gives you a lot of detailed information if you can do it, but it is a lot harder than to study using conductive AFM. So this is an example of one of the hybrid nanowires. This is a palladium coated on top of polyimidazole, which is coated on top of DNA. And the electron micrograph on the right-hand side shows the dark area in the top left, which corresponds to the main mass of nanowires. So this is a spot of nanowires that you can almost see by eye. It's very large, and as that dried down on the surface and the meniscus receded, you get individual nanowires which stretch out from it. Sometimes these are bundled up into ropes of 2 or 3 nanowires, but you can see individual examples poking out. And you can touch those with the conductive AFM tip, and you can measure the current flowing along those wires through to the main mass. And the other thing you get out of this measurement is you can walk the AFM tip along those nanowires and look at how the resistance changes. So as you walk towards the main mass at the top left, the current increases because the resistance decreases as the length of the wire decreases, and this is what's plotted in the diagrams. This is very nice because it lets us estimate the contact resistance. We can extrapolate the resistance to 0 length and estimate the contact resistance, which in some cases is very large. So sometimes the contact resistance in these systems is a significant fraction of the measured resistance, and sometimes it's relatively small. And finally, I'll show you one last measurement technique. So this one is less familiar, but it's the easiest of all of the techniques to execute, because you don't even need to make contact with the nanowire to do this. It's based on something called lift mode in AFM. So I've sketched here how lift mode works in AFM. So you have the cantilever, which is that holds the tip which touches the sample to generate your image, and this is oscillated by a drive piezoelectric. And first of all, you scan along the red line. So the dotted red line, you scan along here, and the tip adjusts its height so that its force of interaction with the sample maintained constant, and it will follow this path illustrated by the dotted red line, and that gives you the topography of the sample. And then in a second pass, it lifts the tip and come back over the same the same line, but just at 50 or so nanometers above, and oscillating the tip along the blue line. So we have a blue line lifted at height h, which is typically about 50 nanometers, and coming back over the same section of the sample to be imaged, and the tip is oscillated. In this case, what you measure is the phase difference between the driving voltage and the deflection of the tip. And you do this with a metallized tip and a voltage applied between DC voltage applied between the tip and the insulating substrate. So the nanowire lies on a thick oxide insulator. So there's a capacitance between the tip and the underlying silicon, and there'll be an energy stored in that capacitance proportional to the square of the voltage. And what happens is that energy is effectively added to the mechanical energy of the cantilever, and it shows up as a change in the force constant K, and this shows up as a change in the phase between the oscillation of the tip and the drive voltage, the phase phi, and that is what you actually image. And the changes to the capacitance between the tip and the sample show up as this phase. Perhaps I will, in the interest of time, I'll just skip to some data. So here's an example. This is one of the very nice looking copper nanowires, and what you see here is the atomic force microscope image in this lift mode. We call it scanned conductance microscopy. So we're not making contact to this nanowire. It's sitting on a substrate of silicon dioxide, so we're not deliberately trying to pass current along it. What we're looking at is the capacitance between the tip, the nanowire, and the underlying silicon. And the effect of the nanowire is to change that capacitance. And it turns out, if you work through a reasonable model, so the paper by a group of authors from the US in 2004 worked out reasonable models for what this phase angle should be for different situations. And there comes to two terms, one corresponding to a term corresponding to the capacitance of a tip above the bare substrate, and the other in pink here corresponding to the tip above the nanowire. And it turns out that for an insulating nanowire, the capacitance above the bare substrate is always larger, and you always see a positive phase shift. and whatever the voltage is, whether the voltage is plus or minus, you always see a positive phase shift because the capacitance effect is proportional to the square of the voltage. So this is how you distinguish this from other effects. So sadly, this tells us that the very beautiful looking copper nanowire is actually completely insulating. It has a conductance less than 10 to the minus 12 Zeeman per centimeter. This technique is very, very sensitive to even the slightest trace of conduction, and it's effectively measuring the differential conductance at zero bias. So unfortunately, this is an example of something that's not conductive, even though it looks like a good copper nanowire. And the reason is that there are probably small gaps between the particles. This is an example of one of our polymers. On the left-hand side is the ordinary AFM image, which is acquired simultaneously, and on the right-hand side is the scan conductance image. And you can see a dark black stripe going across the image that corresponds to the position of the coated DNA molecule. The negative phase shift here demonstrates that this thing is conductive. So the technique is very good at picking up traces of conductivity, but it's not good yet at telling us exactly what the value is. The value was determined by direct current voltage measurements. It's weakly conductive, this material, but this illustrates how sensitive the scan conductance is. And another example, this is Palladium on DNA. Image A is the AFM image, which is an ordinary AFM image in tapping mode, which is acquired at the same time. And that just shows the height variation. You can see 3 thick palladium coated nanowires, and you can see a lot of bare DNA molecules in between. And B and C correspond to scan conductance images with positive and negative bias voltages. And what you can see is the palladium coated nanowires are strongly conductive with this strong negative phase shift, and the bare DNA molecules show up with a faint positive phase shift, which illustrates that they're insulating. And last slide. This is another illustration of some of the power of this technique. This is an example of a very badly prepared silver DNA sample. So this was a sample that was prepared under conditions where you get a lot of material that is off the template, probably had too much silver here, but it shows an interesting thing. So we've got on the left the regular AFM image, and you can see a thick sort of a nanowire in the middle, and you can see lots of little particles of silver everywhere. But the question is, are they connected? And if you look at the scanned conductor right, what you can see is that only the ones that are connected show up with a negative phase shift. So the 2 red arrows illustrate sequences of silver particles that are actually electrically connected, because you can see the dark areas in the image on the right hand side. Most of the small silver nanoparticles throughout this image are not connected, and they don't produce this negative phase shift. Okay, so that's all I wanted to say. I just finished by thanking my co-workers over the years, Andy Hulton and Nick Wright. So Andy Hulton in chemistry, Nick Wright in Lechenge, Bernard Connolly from biochemistry, and all the people below are former PhD students or current postdocs with my group in Newcastle. I'd like to thank the European Union for funding, and also the EPSRC and Intel for funding as well. So thank you. Does anybody have any questions they would like to ask?
Okay. Yeah. Okay, thank you very much, Dr. Ben, for the very interesting work. I'm sure that it's a lot of effort to work on it. And then here, I think also so many questions they would like to convey to you. And then maybe anyone else, if you want to ask the question, maybe you can just open the website in the www.menti.com and use the code data that already display in the screen. So maybe Mr. Adi, could you please share? Okay, it's already. So Dr. Ben, this is the first question. How to keep DNA not to split into the fragment when we are entering metal?
Well, we looked at this aspect early on. So, for example, in some cases, metals are known to cleave DNA, but we're working at relatively low concentrations, so we don't typically observe this as a problem. Many of the polymers we make are polymerized by oxidation with iron chloride, and we did do control experiments to see if the iron 3 would damage the DNA, but it doesn't appear to damage it at the concentrations that we use. After the material has been templated, it's very hard to know whether the DNA is split or not, although we tend to see nanowires that are longer than the original template and not so many that are shorter. So I don't think that it is a major problem. Maybe if in terms of breaking the DNA.
Okay. But you didn't do any experiment like how if the DNA split into a fragment and then what is the electrical conductivity will be?
We looked for fragments of DNA. When we started this, we looked to see if some of the chemical reagents would break the DNA. So we did things like gel electrophoresis, but we didn't see much breakage of the DNA. It's a relatively robust molecule, the double strand.
Oh, okay. So the next question.
Okay, this depends a lot on the material. So hard metals will mainly bind to the phosphate groups, and some other metals will interact with the nitrogen atom of the bases. A lot of this, there's quite a big literature, of course, on inorganic coordination chemistry with DNA, and so our best evidence for what any individual metal is doing comes from things like FTIR spectroscopy, because you can see shifts in the positions of the bands of various vibrations. The conductive polymers are a little bit interesting because the shape of the oligomers that you make for those is very similar to minor groove binding drug molecules. So we think that what is happening with those is that they are initially binding in the minor groove in a similar manner to, flat aromatic molecules that are known to interact that way. But we think the metals are mainly going for phosphate and nitrogen atoms.
Okay. Okay, next question. Not yet. Okay, maybe. Is there any specific metal characteristic which we can use?
The biggest limitation of this whole process is that DNA is basically only soluble in aqueous solution. So you need a metal which you can find a stable salt in water and that you can reduce in water. So things, most of the noble metals possible. Some metals, for example, we at one point tried to make bismuth nanowires, but we just ended up making bismuth oxide because it's hard to prevent the oxidation of elemental bismuth when it's produced in nanoparticle form in water. The other limitation of the technique is that there are some materials for which the reagents are just not compatible with water. So I don't know of any way to make silicon nanowires by this method. There are other ways of making silicon nanowires, but all of the silicon reagents that I can think of are not water stable, and I don't think that you can do this with 3-5 semiconductors either. So the main limitation is can you make the chemistry happen in water, because it's not easy to get DNA into other solvents. Some people have explored putting DNA molecules in a vacuum chamber and evaporating metal and that kind of thing, but at the high temperatures involved, you might actually break the DNA there.
Okay, next question. Must the metal be nanoparticles?
Well, I don't quite understand. I mean, what we think happens is that the metal ions bind to the DNA, and then they are reduced, and they nucleate on the DNA, and so they nucleate as approximately spherical particles just because of surface effects. And it's only when you completely cover the DNA that the thing starts to transform towards a nanowire. I have to say that we find that it's actually harder to make metal nanowires by this method than it is to make polymer nanowires, and that's probably because of the surface tension. So the copper nanowires that we first made about 10 years ago, they're really not conductive at all, and it took quite a lot of effort to find ways to force the copper to make a smooth nanowire, because metals like that have very, very high surface tension, and so they really don't want to be nanowires. They'd much rather be nanoparticles. You have to reduce the surface tension somehow.
Yep. Okay, next question.
I don't know. We have tried making sensors, so we published some measurements of hydrogen sensing using palladium nanowires. Essentially, you can make a device where instead of putting a single nanowire down, you put a large number, a network of nanowires, and you make 2 contacts, and you look at the resistance of this device as it's exposed to hydrogen. So hydrogen will insert into palladium metal and increase the resistance. And so we did some sensing with these things. I think they have advantage in this because they have a very large specific surface area. So it's quite difficult to make highly conductive nanowires by this process. So if you want very high applications where you need very high conductivity, then it's not necessarily the best way to go. The nanowires we make are very, very thin. So they have high specific surface area, so we suspect their best application will be in sensing devices. So I have some of my students have worked on sensing of organic vapors using, for example, some of the semiconductor nanowires.
Okay, next slide, please.
Depends what you want to do with it, I suppose, but in terms of how smooth they are, how easy to make, and sometimes even how conductive they are. The polymers tend to be better. They have, because they have a low surface tension, it's much easier to persuade the polymers to coat the DNA uniformly. So that in terms of metals that we have managed to make highly conductive, there's silver and palladium are the two. But many of the other systems, copper you can make conductive, but it's really quite difficult. Other examples, the conductivity of the metal is typically many orders of magnitude lower in nanowire form than it is in the bulk. So we've made iron, rhodium, and silver, palladium, copper. And out of those, I think only really silver is highly conductive. Palladium is reasonably conductive.
Okay, the next slide, please. What is the function of ascorbic acid? I think in the slide when you
yes, I'm sorry.
Yeah.
I didn't realize that I was
Produce
mute.
nanowire, yeah.
So the way you
copper
make
nanowire,
the way you make the it can be replaced by other reagents, so it's a reducing agent. So the process involves addition of copper nitrate solution to a solution of lambda DNA, and then you add a reducing agent. And in that example, we used ascorbic acid. You don't need a particularly powerful reducing agent, but you could use any aqueous soluble reducing agent. Borohydride is also possible. We used that for palladium. Dimethylaminoborane we have used as well. But for copper 2+, we found that ascorbic acid is sufficient.
All right. Okay, next slide, please. Next question. Next question. Okay.
We haven't, well, what we did eventually to make copper nanowires, eventually we went to a non-aqueous process. So we worked with copper 1 diacetonitrile anion, and it does have an effect. So yes, you can, changing the solvent and changing the anion will have an effect on the reduction process. I don't fully understand why, but it does.
Okay, next question. I think maybe it's from your slide presentation when you slide presentation that you send us, yeah.
No, it's just regular powder X-ray. If you look at the data there, it's quite noisy because we don't have a lot of sample. So there's two. So it's just a standard powder X-ray diffraction instrument, and you either have to do one of two things. You have to speak very, very nicely to the powder X-ray service technician and persuade them to integrate for a long time in order to get the signal to noise ratio up, or you have to use an alternative sample of DNA which you can obtain in much larger quantities. So sometimes we use calf thymus DNA, which is available in much larger quantities than lambda. It's not as pure, it's not as monodisperse, but you can easily supply 50 milligrams of sample for powder X-ray measurements if you're using calf thymus. But it's just a regular instrument. You just have to either use larger samples or you have to integrate for a long time to collect good quality data.
Mm-hmm. Okay, next question. What is the difference in electrical conductivity between thin nanowires and thick nanowires? Thin and thick.
Well,
and which one is better?
So it depends a lot on the material. So we were funded by Intel at one point, and they were interested in copper. And of course, if the nanowires I showed today, they're examples of ones that are very thin. They were about 5 nanometers in diameter. They look very beautiful in the AFM images, and they don't conduct at all. We can't measure any conduction at all. And the scan conductance microscopy is very, very sensitive. So I think when the nanowires are very thin like that, you have a tendency to have breaks somewhere along the length, and that spoils the conductivity. So in the case of copper, we eventually made conductive nanowires by finding methods to increase the thickness, and also we switched to a non-aqueous solvent. So sometimes it helps, but sometimes sometimes the trying to make very thick nanowires, sometimes it just fails, because if you exceed the amount of material that corresponds to a stable nanowire, then it prefers to be particles. So it's very much analogous to the way a stream of water will break up into droplets. So you try and, if you increase the thickness, eventually the thing just doesn't want to be a nanowire anymore, because it's not really feeling the influence of the template. So I don't think any of our nanowires are thicker than about 15-20 nanometers. And occasionally we see thicker objects, but it's always turned out that they are not single nanowires, but more like ropes, where multiple strands of DNA are wrapped around each other and then coated with material.
Okay, next question. Is the linear energy affected by the polarity of the constituent component?
Well, yes. Anything that increases the adhesion of the material to the template will help. So, so anything that increases the interaction of the material with the phosphate groups or the nitrogen bases will help. And in fact, you can control this when we did some work making hybrids. So if I form a conductive polymer first, I tend to get a very smooth nanowire, and if I change the monomer so that it has a ligand attached to it, then sometimes that ligand will interact very strongly with a suitable metal ion, and then you can make a smoother metal nanowire by first coating with polymer and then bearing a ligand and then coating with metal.
Okay, thank you very much. Is there any next question, Mr. Adi? Finished, right? Okay. Oh, okay. Which one? I think it's already answered, I think. What is the interaction between metal and DNA template when DNA template nanowires is generated? I think it's already answered by Dr. Ben.
Well,
Okay, so yeah.
okay, I think I suspect the question is about what's happened after the metal has been reduced, after it's been reduced to the element.
Yeah.
And
Okay.
short
Yeah.
answer is I don't know. It's very hard to say.
All right.
Once the DNA is coated, it's quite hard to interrogate that. We still see shifts in the infrared bands of the DNA. So it's possible that in some cases there's a small amount of metal which is still not reduced to the element on the inside, but it's very hard to be sure.
Okay. Yes, all right. Finish.
Infrared spectroscopy is probably the only probe we have of this. Yeah.
Next question, still there? Still 3? Oh. What is, how far is your research result from future application? Okay, I think this one. How far is your research result from future application of this nanowire? What is the next step you will do to reach it? I think for the next research.
So we've tried, well, in terms of applications, most of our effort has gone into sensing technology. So the reason that we went for that is because there are many applications of nanowires, but in sensing technology, you want something which where the material responds very strongly. It changes its resistance or its conductance very strongly in response to the environment, and it doesn't necessarily have to be a highly conductive material, right? So to make a good sensor, it's more important that its conductance changes very strongly than it's particularly conductive. So that's what we've spent most of our effort on. The biggest hurdle is probably obtaining large amounts of pure DNA. So there are now companies which have developed methods for producing very, very pure DNA by enzymatic processes, and so we think that is that's one of the most important steps in this business, to be able to produce large amounts of this, because Lambda DNA you typically purchase 1 milligram from New England Biolabs, so that will cost you a lot of money. So the biggest hurdle, I think, was obtaining pure DNA in large quantities. And there are now new sources of DNA which may help us overcome this.
Okay. Okay, finish. Okay. So finish. I think a lot of questions. So meaning that your presentation is very, very interesting, Dr. Ben. So thank you for sharing about your research, and yeah.
Thank you very much for inviting me to talk.
Yeah.
Hope things are okay there.
Yeah. Dr. Ben, I think do you know Miss Triwindarti? I think
yes, I saw her name in the yes,
Bu Triwindarti, are you there? Maybe you can talk to Dr. Ben. Just say hello.
Dr. Ben, good to see you again.
How are you? You working on
calcium phosphate?
Oh yeah. Dr. Ben, maybe I can close this webinar series first, and then after that we can talk. Okay. Yeah, I think Oh, okay. Oh yeah. First we will make a photo together. So please open your video for all participants, please. so we can get a photo together. Pak Adi, ready? Mr. Adi, finish? It's okay.
All seated, yeah.
Okay.
Just one, two, three.
Yeah. 1, 2,
1, 2, 3.
3.
Okay, thank you.
Okay, thank you. So thank you very much for all participants here, and see you in our next webinar series. So bye bye. Wassalamualaikum warahmatullahi wabarakatuh. See you all. And Dr. Ben, Miss